thinking about it. There we go. Okay, welcome back. I'm pulling up like calendar for like logistics. Goal is today wrap up homework 1, and then 9/16. That would be next Tuesday. So Friday, think about like what did we learn from these last couple of weeks, and what are some questions that should be on quiz 1. So that'll be next time. And I think we can do it. And so we had 210. We did some rocket work. I think 211 was the last part. Okay, so in 211 we have Galileo's claim. Galileo is the father of like kinematics, so he was the first person to kind of think about motion as like describing motion with math. So according to Galileo, everything, no matter how big or how small, it all falls at the same speed. And he did this with like ramps, kind of measuring things as they rolled down ramps. But in practice, this isn't true like all the time. Like sometimes there's stuff that moves faster than other things, not because gravity's different on them, but there's something else happening. So the question is here, how do you show, like how can we use like a free body diagram and what's called an equation of motion, so actually like taking that sum of the forces, saying it's equal to ma. How do we show that there are other things at work, and specifically like what is the cause of slowing something down? Like how does it change the speed? Do heavier things always move faster, or is it smaller things are faster? So that's what we're trying to figure out here. So what do you think? Where would you start with this one? Yeah. Drag. So what do we do with drag? Okay. Yeah. And what is drag doing? Like how do we, so we can write like drag, we have an equation for it, but how does that tell us what's happening? Yeah.
It's going to oppose the direction of motion directly.
Okay, so where's our direction of motion?
It's going to be down the slope.
Where's all the other? So is that the only force acting on it? No? Do we have other things? So maybe here, a free body diagram. Where's the drag acting? Make a free body diagram, hey. Yeah, exactly. So start off, and for the most part, anything to do with like motion or forces like that, always start with a free body diagram. Sometimes it doesn't give you a lot of information, but it's always a great starting point for any of these problems. So let's try that. And I heard like a slope. Do you want to consider a constant slope? Like a ramp? We could do that, yeah. All right, so we got our skier going down a constant slope. What are the forces acting on the skier? So far, this is what I've seen so far. You can some kind of drag, maybe there is some kind of contact, right? So maybe there's friction. If the skis are kind of well waxed, shouldn't be a lot of friction, but could be there. Other forces? Or is that enough? Yeah. Okay. So is there, yeah, so is there some kind of like driving force on the slope? What do we think? So there's two parts to that. So one is that like if you're constantly using your poles to keep pushing forward, then maybe you do want to say that there is like an extra, like every 2 seconds there's an increase in momentum or something. Or versus like the initial push off, like out of the gates shoving off, where that's an initial condition where I know the initial position was top of the slope and the initial speed was maybe 3 miles an hour as you push out of the gate. So that initial push, you can say it's an initial force, but it's an initial kind of like very short time period force where it only lasted for a second or so. So usually what we do is call that like, I know there's an initial speed. That's my initial condition. But yeah, that's usually how you kind of handle that. What does MA look like? Where's all of our acceleration? Do we need multiple components, like an X and a Y? Maybe? Where are we going? Yeah. Oh, so keep it. So that would say we've got X and Y like this. And then we've got a forward and a downward. We could do it that way. End up doing a little more trigonometry, which, I mean, I know we're all like, that's what we're here for. More trig. That's what every semester students complain on the evaluations of, like, there just wasn't enough trig. That was the problem with all of these engineering classes. What do we think? Good, have an AX and an AY. Now we have two equations, right? Acceleration X, acceleration Y.
Is there a way to determine where the leader of the arrow is going, whether it's pointing into the point or out of the point? Is there a right or wrong way to do that?
Oh, if the force is pushing like into the dot versus pulling the dot?
Exactly.
It doesn't really matter, because the only thing these vectors, these arrows are representing is a magnitude and a direction.
Okay.
And in this case, we're not even really keeping track of magnitude.
Yeah.
We're just looking at direction, like which ones are lined up, which ones have components on top of each other. Yeah, so whether it's pushing or pulling, it's not a 6 of one, half dozen of it.
It'd probably be easier if we change our coordinate systems so that positive and minus come.
Yeah, maybe like just rotate just a little bit. Like what if instead we call it X and Y, because now our height, we're always on the slope and we're not leaving, so the only thing we need to keep track of is like how far down the slope we've gone. Just changing, just rotating that coordinate system just to match up with the path of the motion. Nice part there is that we have like all of our MA in one direction and then it's 0 in the other direction. So right now we've got like 3 things pushing us down the slope. Well, 1 thing pushing us down the slope, gravity. 2 things pulling us up the slope, friction and drag. Does friction, are they both changed by how heavy we are? Heavier person, more friction? So heavier is slower. Is that right? Heavier person, less friction. Heavier is faster. What? Friction depends on something else? Okay. All right, so let's look at 3 cases. All right, if there's no friction, no drag, what is MA equal to? No friction, no drag. How much acceleration do we have? Yeah. This is how I like to approach things. It's like, if I think one thing's a problem, add it one part at a time. So we'll start off with no friction, no drag, and then just friction, and then friction, drag.
Is it gravitational force?
Gravity. Yeah. So we'll have like some component of gravity pushing us down. How much gravity is pulling us down? How do we want to describe that? mg?
Yes, no, you're going to go down anyway.
Mg cosine.
Some kind of
Where you're going to go.
cosine of the angle? All right, so we'll call it theta.
Yeah.
That we're going down a slope of theta. So if theta is 0, then there's no acceleration. Or wait, theta is 0, there's that it's equal to. Then we would be free falling, at least with cosine. So sine. Okay, so we'll get rid of m on both sides. So A is g sine theta. There's no sine. So in this case, if there's no friction, no drag, it's exactly what Galileo said, right? It doesn't matter how big you are. You will always go down the slope at g sine theta. So 45-degree slope, it's 9.81 over square root 2. So I don't know, 6 point something meters per second squared. So we still have mg sine theta. What about friction? We're going to say mu is not 0. It's something, it's a constant, like it's some value, but it's not 0. What does that one look like? What happens there? Added to? Subtracted? Added to and subtracted.
You gotta take the force, the force, I guess, you're accelerating, you have to like subtract it by the force of force, there's no gap directed.
Yeah, so here, if I, and this is why I draw a free body diagram to start. Force of friction, I drew up the slope, which is a negative x direction. So negative force, so it's always a negative mu f, like mu mg something.
So yeah, the opposite way time, it'd be mg sine theta
And then
minus, I guess, you know,
normal force, yeah, mu times the normal force. So in this case,
force is also an angle compared to the thing, so it wouldn't exactly be.
yeah, well, normal force is along our y-axis,
Yeah,
which
so
is nice.
So I guess
The cosine?
yeah. So
Yeah, so overall, like our sine component is our downward acceleration. Our cosine is that normal force. Like it's 90 degrees to it. Because sine and cosine, they are the same function, they're just offset by 90 degrees. And sine squared plus cosine squared equals 1, so it's always our two components. If one component's sine, the other one's got to be cosine. That one's kind of, again, like just speed running through our trig lessons, which there's never enough trig, never enough time for trig. All right, so now take M, divide through each one, and I have, yes, A is now G sine theta minus whatever friction value, so some component of friction is slowing us down. What if I'm 100 kilograms versus 50 kilograms? Any difference with friction?
The mass can cancel out, so.
Mass canceled out, right?
You still accelerate in speed, right? No matter what mass you are.
Yeah, so with friction, and this is something, I feel like intro to physics, like a lot of times you sort of throw your hands up, like things are different because of friction. It's like, no, like friction has a very specific effect, and like it's always proportional to weight, and so it doesn't actually, there's no change in time of friction. It's just like this constant slight change. It just removes energy at a slow rate. So in this case, it has no effect. It slows us down slightly, but there's no effect on like weight in this case. If that makes sense. So that did nothing for us. We have no new information because we still agree with Galileo. You look like you don't believe me.
No, I'm just looking at y is there cosine. Because if we're aligning the x and y plane with the slope, wouldn't the angle not matter if it's going? Right, but the angle would only matter for gravity if we're aligning the x, y with the slope.
It's always got to be normal to our slope.
Yeah, no one works big over slope, no gravity to angle, so it's like a line, not just like gravity by.
Yeah, like if
That's for gravity, I'm saying like for friction.
Friction? Well, the normal force is, just practice.
so kind of making like a 45-degree slope. Now we can see, oh, that one's not really. Let's line it up here. Like if the bigger the incline, the less normal force you have, to the point where like if you're on a vertical wall, you can't have friction because there's no normal force pushing you against the wall. Well, yeah, you're just free falling, yeah. And you can try to like kind of grab onto it, but there's nothing falling down on a vertical wall. There's no friction there to slow you down. Does that kind of make sense? No? That's okay. It doesn't have to. Yeah, okay. All right, so now, the Hail Mary. We have our G sine theta. We have, M minus M mu G cosine theta. What about drag? How do we add drag into here? Which one? The drag? Subtract, okay. All right, so let's subtract force of drag, and I'll just plug in this equation. Do you know what all these terms are? CD, rho, A, V. Yeah. What is rho? Sorry, not which symbol, but what is it? Okay, so rho is our density of the fluid that we're moving through. So that one, no matter what, doesn't matter who we are. We're all moving through air as we ski. I guess unless you're on Mars or something, then air is different, maybe different density, probably similar. So rho is density. I wrote CP, it should be CD. What is CD? What is that one? I know now we're talking about like aerodynamics. The coefficient of drag. What are coefficients of drag? Like how big do they get? Ballpark. Can they be 100? Is that a big or a small coefficient? 1? Yeah, I mean like a parachute might be 5, but most stuff is probably 0 to 1. Like if it's just a normal person going down a slope, it's probably around 1. If you're aero, like Ned Flanders in his like tight ski suit, then it might be 0.8. Let's call it like, that one's about 1. What's A?
Surface area, what is the area?
It is an area, and this one's weird because it's not like total surface area. It's the cross section. Oh, sorry. Yeah, it's cross sectional area. So, like I think about it a lot. Like riding a bike, and if you're upright with your hands out like this, you have a big cross sectional area versus tucked in, elbows tight. You can reduce your cross sectional area. It reduces drag. So that one's cross section. And it's specifically like, what does the fluid see as it moves past you? So it doesn't really matter sideways. If I'm moving forward, it doesn't really matter how much area is this way. It would be like, how big is your shadow almost if you had a backlight on you. Okay, and then what about V? What is V? Velocity. So our current speed, how fast are you moving? And I said speed because we're squaring it, and so even if it was velocity, it's still, we take square, so it's just like magnitude squared. Okay? Do the same thing, take mass, remove it from all these terms. Do any of these variables that we just went through depend on the mass of the person? Last one? The speed? Oh, or the
Well, I guess that's what,
density of fluid, yeah. Not the fluid of the person, like fluid that person is moving through.
yeah.
None of them are directly, some people have brought up the point of like, hey, a bigger person has a bigger cross-sectional area. Yeah, and it is true, like 190-pound adult has a bigger cross-sectional area than a 50-pound child. But they could both kind of tuck down into similar shapes, and volume scales a lot slower than area. Right? Or volume scales faster, sorry. Volume scales faster than area. So you need a lot more volume to get to same cross-sectional area. Are we done? Do we prove? So one thing we could like have a ridiculous thought experiment of like, let's make the skier just pack, instead of wearing like cotton, everything's lead. Just basically compared to every other skier, that person is infinite weight. Then what would happen to the force of drag? It becomes zero because we have a 1 over m kind of term. Versus the opposite of like what would happen if this person like was a wraith of just like almost massless. What happens to force of drag is like this person loses all, keeps going up. How big does it get? How big is the force of drag on like a massless person? Same cross-sectional area. Or you could say that it's smaller, but infinite. Yeah, so you could have like, if there was literally no mass, but still a cross-sectional area, which is kind of what we see with like a feather. Big cross-sectional area, very little mass, lots of drag, like a big effect of drag. It's not that it has like a bigger drag force, it's just the effect of drag is much bigger. Yeah. I guess really we should say 1 over m. That we have like, you'll hit that terminal velocity much quicker, something like that. That's one way, but if you have a different, if you were thinking about this in a different way, or if you want to like plug in numbers, that's a great way to think about this problem. Questions? Good. Yeah.
What's the n under the b squared for it?
Over here. Right. Like this one. What is that m for? As it catches up. That one is because in the first two, in like equation 1, equation 2, we divide by m, and the m's all cancel out. Equation 3, we divide by m. It still cancels out in those first two terms, but the last one doesn't have, there's nothing that directly depends on m. So we have to divide through by that. We have to leave that 1 over m times v squared in there. Yeah, and that's how we end up with like bigger accelerations with smaller mass, or like, or smaller accelerations, bigger, smaller mass, things like that. Okay, so now we've got one last problem. They all look similar, like similar kind of a block on a surface, but 3 different forces applied to this block. And this is where we'll, so in this last problem, we looked at, this is, when we came up with this term, A equals this, that's called our equation of motion. So it's described, how does acceleration depend on, it could be position, it could be time, it could be velocity. In this case, it's just velocity and time, like a constant thing. So now we want 3 equations of motion, and then we'll use then I'll show you like 3 ways of solving these differential equations. Make sense? Who has taken an ODE class, like a differential equations class? Everybody? All right, so this is like, you're golden, you're fine. All we need to do is find the differential equation, and you go through, then we'll solve it. first step is always free body diagram, right? So what do these 3 free body diagrams look like? I drew them all as 3 dots. If you want to write, if you don't want to put the square in there, okay. Here's a damper. Yeah. That one has a fluid inside of it, so you can slide back and forth. The faster you slide, the more force it's applied. That one's just showing you like this is a positive x-axis. So I'm showing you what you can use as a kinematic. Yeah. In B, C, we would say that it's frictionless, and then A, we're saying there is an effect of friction. I mean, I guess you could add friction, and it just makes it harder to solve in both cases. In B, so B is called a damper. It has like cartridge and oils that kind of fluid. So the faster you fill it, the more force it's applied. That's like 3/4 how they swing fast, slow down, damper something, and then shocks and stuff. It's all spring back damper. Yeah.
What did you put in C?
Oh, it's still no force or thinking. That one's just showing you like positive x as direction and axis. Yeah. Yeah. First, we did the free body diagram. So we kind of created an equation, and then we can say what is x itself. Yeah, but the thing is changing. You also need to find oh, this one's just like on a surface, like on a table. Yeah. That's okay. So that one's called a damper. Right, like it is.
Do you remember,
And so there was, again, kind of coming up with that question, like, do we need a forward force to say that it's moving? And it's like, well, no, because the only thing really acting on it is that force of friction. Like, that's the applied force. The fact that it has an initial speed, that's that's our initial condition. Like, it's not a constant force applied to it. So friction, opposite its motion. This one stumped. I mean, I say stumped, but really it's just like, I just haven't seen it, so why would I know what that is? This thing is called a damper. You see these are all the time, like shocks in cars, bikes, motorcycles. They're always kind of these like housed things. So in the internal of it is like a mesh plate moving through some kind of like oil or fluid. And the faster you move that plate, the more force gets applied. So with that, we can call it kind of like an FB. And it's, in this case, we're just gonna say it's a linear damper. So B, the force is B times V. The faster you move, the bigger the force. So linear. That's why it's linear, because it's proportional to speed. What about spring force? Where is that one pointing?
also towards the spring?
Towards the spring? I like that one. Oh, it depends. Okay. All right. It depends. Does it depend? Is it compressed? Is it stretching? So do we need multiple free body diagrams? One for stretch, one for compress. What's the, like when we say, what's the Hooke's law for a spring? Like what's the spring force? Oh, that one's potential energy. Yeah. So derivative of that is Hooke's law. So negative kx, yeah, we could call it negative kx. So here, this is, and again, I'm showing you how I do it. I follow a lot of standard. There's some stuff that I do that's my own preference. This is mostly standard. It's a good way of doing it. On the diagram above, we have, in all three cases, x to the right. So if displacement is positive, Fs is negative. That's what I drew on my diagram. If I have like negative displacement, so if I'm compressing the spring, then I have a negative x. So I can still say that it's Fs to the left, but it's a negative Fs. So it takes care, so the sign convention takes care of itself. So I can say Fs is Kx, it's just a negative Kx, so it's pointing in that left direction. Does that feel okay? Or dirty? It's like, no, we need two free body diagrams. This is crazy. 3 cases, all 3 of these are differential equations, A, B, and C. They're all first and second order differential equations. I'm looking at time. We have 4 minutes. 4 minutes. That doesn't feel like enough, but because I wanted to like plot it, like solve it, plot it. Should we finish on Friday? Just push off due date and finish, so then we'll have time to like actually think about solving it and plotting it, and then submit. We could push it off to Friday, but then you have to submit it. Or we could push it off till Monday, then we'll build the quiz Monday. That way you can like absorb and submit rather than submitting Friday night. I don't like Friday night submissions personally. It's like I got stuff to do. I got a family. I'm trying to get out of here. Let's do that. Sound good? Usually there's no complaints of pushing off due dates. There's always like a small population that's already done, but such is life. Okay, thanks a lot, and we'll pick up here on Friday.